Hello. In this particular session, let us discuss how the speed of DC shunt motor can be varied by using armature resistance connected in series with the armature. So in the last session, we have seen how the speed is varied by varying the flux, that is by flux control method, which is also called as field control method. In flux control method, the flux which is produced by the field winding was varied so that the speed of the motor we can able to control. That means what I can tell, by varying the flux, the speed of the motor can be varied in case of flux control method, and which has got a limitation for the maximum speed. That means the speed of the motor can be varied, can be increased above the rated speed. Limitation is for the maximum speed. There is a limitation for the maximum speed which can be obtained, that is above the rated speed. So in this particular session, let us discuss how the speed of the DC shunt motor is varied with the help of a resistance which is connected in the armature circuit. So now you can observe the circuit diagram which is shown. So here, as usual, we are having a supply voltage comes in parallel to the field winding. Again, it comes in parallel with the armature circuit, which represents a DC shunt motor, which represents a DC shunt motor. But here what we have done, a resistance, you can observe a variable resistance is connected in series with the armature circuit, so it is called as armature resistance control. So if you try to recall the equation of speed which has been derived in the last session, we have taken a back EMF equation. We have taken 5Z NP divided by 60A. Yes or no? In the similar way, another equation by applying KVL to the DC shunt motor, we have obtained another equation, that is EB is equal to V minus IRA minus armature reaction drop minus brush contact drop. So by comparing these two equations, we got a equation representing the speed, that is speed is directly proportional to V minus IRA divided by flux. So by observing the parameters of the equation, we have come to a conclusion that by varying three parameters, the first one is the flux, we can change the speed. The second one is the resistance RA. By varying RA, we can change the speed, and by varying V, that is the supply voltage, we can vary the speed of a DC shunt motor. In that, here we are concentrating on that particular RA. Actually, RA is the resistance of the armature circuit, which will be very small, But here we are not varying RA. Indirectly, we have connected a resistance in series with the armature, and we are varying the armature circuit resistance. We are varying the armature circuit resistance so that the armature voltage gets varies. As the armature voltage gets varies, automatically the speed can be varied. So here we have to concentrate on the voltage which comes across the armature, So here, what is the voltage which is appearing across the armature is nothing but the supply voltage minus the drops. Minus the drops. We have derived EB. The EB is the EMF which is induced in the armature. That one we have seen. What is EB? EB is equal to V, this supply voltage, minus IRA drop, that is the drop which takes place in the armature resistance, minus armature reaction drop, ARD we have seen, minus brush contract drop, the drop which takes place. The resultant of those voltages was appearing across the armature. So now we are trying to vary that voltage and we are trying to establish the speeds at different armature voltages. So as usual, if you observe the circuit diagram you can observe V is the supply voltage, a DC supply voltage, a field winding which produces the flux which creates the magnetic field in the motor, and RSH represents the shunt field winding which is of large value. So the ISH will become constant, the voltage is constant, therefore ISH will become constant and flux remains constant, so it is called a DC shunt motor or a constant speed motor also we have seen because the flux remains constant. If you recall the speed current characteristics, you will come to know that a DC shunt motor is a constant speed motor, right? So now what we have done, if you come to the armature part, the armature resistance, we are trying to vary the armature resistance by connecting a rheostat in series with the armature. So whatever the voltage which is coming across the armature has to be varied in order to vary the speed. Let us see that. So coming to the graph, if you observe the graph, as usual the y-axis we have taken the speed, the x-axis is the voltage, that is the rated voltage. This is the voltage which is applied to the armature, the voltage which is applied, you can take the rated voltage which is applied, that is the supply voltage. Whatever the voltage we have applied, you can consider that voltage, that is the V rated. So x-axis we have taken the armature voltage. The variable parameter is the armature voltage. VA represents the voltage across the armature. So N rated is nothing but the no load speed or the rated speed of the DC shunt motor we can consider. N rated is the rated speed of the DC shunt motor. V rated is the rated voltage which is applied to the DC shunt motor. So here if you observe, whenever the voltage, a rated voltage comes across the armature, at that time what was the speed? The speed was a normal speed. The motor was running at the normal speed, you can observe. So when voltage across the armature x-axis, if you observe, when the voltage was V rated, at that time if you observe the graph, what is the speed? The speed is normal speed or the rated speed, what I can consider. So what is happening, as the voltage across the armature decreases, if you observe, decreases, the speed of the motor actually it is decreasing, you can observe. Earlier the speed at rated voltage, the speed was normal speed. Later on, as the voltage decreases, if you observe the graph, the speed of the motor gradually it is coming below the rated speed, So now you can analyze the graph with the value of resistance, Now let us assume the resistance is 0. That means the pointer is pointing at start position. At that time, what is the voltage we are getting across the armature? It is nothing but the rated voltage. So when R is equal to 0, what is the voltage I am getting across the armature is nothing but a rated voltage. Whatever the voltage I am applying, entire voltage comes in parallel with the armature, therefore the rated voltage. So at rated voltage, if you observe what is the speed, it is normal speed, because The speed of a DC shunt motor is directly proportional to the armature voltage. Is directly proportional to the armature voltage. Inversely proportional to the flux. Inversely proportional to the flux. We are concentrating on armature voltage, keeping the flux constant. Here we have kept the flux as constant. You can observe the field winding is constant, resistance constant, current, therefore the flux remains constant. The variable parameter is the armature, therefore the speed of a DC shunt motor in case of armature resistance control is directly proportional to the armature voltage. Therefore, at rated armature voltage, the speed is normal, rated speed. At R is equal to 0. Important point we have to remember, at R is equal to 0. Now, let us increase the value of resistance slowly. Let us include some amount of resistance. Let us assume we have included this particular pointer. The pointer is at this particular position, we can take some amount of resistance has been added. Now, if you observe what is the speed of the DC shunt motor. So now, what is the voltage now I am getting across the armature? Earlier, when R is 0, at that time I was getting a rated voltage. Now I have included some amount of resistance. Therefore, what will happen? I will get less amount of voltage at the armature. I will get less voltage than that of supply voltage because some amount of drops takes place in the resistor. Some amount of drop. I can consider that drop as IAR drop. IARA drop is different. IARA drop, it is the drop in the armature resistance, the drop at the armature resistance, that is IARA drop. Other than IARA drop, we have to come across another drop, that is IAR drop, which takes place in the external resistance added in the armature circuit. Therefore, what is the resultant voltage I will get? That is less than the rated voltage come across the armature. As the voltage across the armature decreases than the rated, then the speed is directly proportional to armature voltage. Therefore, the speed starts decreasing. Why the speed decreases? The armature voltage decreases. Why the armature voltage decreases? Because some amount of drop, extra drop, actually it is taking place in the armature circuit. In the armature circuit. Okay, so now further if I increase the value of resistance, further the voltage decreases. As the voltage further it decreases, further the speed of the machine starts decreasing. You can observe the graph, why the graph it is decreasing linearly the armature voltage actually it is decreasing with respect to increase in the external resistance value which is connected in series with the armature circuit. Okay, so now as the value of resistance increases, what I can tell, the speed of the motor it decreases linearly from the rated speed, that is the important, from the rated speed. So this is regarding the armature resistance control or the rheostatic control of DC shunt motor. So again, if you observe a similar discussions has to be made, a small change what he has made is instead of rheostat he has placed a potential divider, that's all. Instead of rheostat a potential divider has been placed. So now as usual you can discuss this particular discussion with the similar manner whenever again the armature control, because the armature is in series with the rheostat. Whenever the pointer was at start position here, at that time what is the voltage across the armature? It is 0 because short circuited. You can observe the A2 terminal, if you observe it comes like this. You can observe the pointer. Let us place the pointer here. It is a short circuit point. Therefore, whenever the armature gets short circuited, what is the voltage across the armature? It is zero. Whenever the armature voltage is zero, what is the speed? Here you can observe it starts from this particular point. Theoretically, it is zero because speed is directly proportional to Va, what we have discussed. Therefore, whenever Va is zero, the speed should be zero. But here it is not starting at origin. The graph actually it is not starting from origin. Sorry, it is starting at some particular point of voltage, that is Va. Some voltage you can observe. That is some amount of voltage actually it is required in order to overcome the inertia, friction and IRA drop. A small amount of voltage actually it is required in order to start the motor. A small amount of voltage in order to overcome the inertia, the opposition force, the friction force and IRA drop. Now, whenever it overcomes this voltages, it drops, then the speed starts increasing. Then the speed starts increasing. So what we can tell, we can start the analysis from this particular point. Therefore, whenever the voltage is zero, we can consider the speed is zero. We can consider speed is zero. Some amount of voltage, this one we have analyzed. It is required to overcome the losses, drops, to overcome the drops. Okay. So at this particular point, the speed is zero. Now slowly I will increase the value of resistance like this. Now I have placed at this particular point. Whenever some amount of resistance we have included, then some amount of rated voltage, some amount of that come across the armature resistance. That means a fraction of rated voltage will appear across the armature circuit. Now the voltage has increased. Earlier at particular start point the voltage was zero. Now some voltage actually it is coming across the armature. As the voltage increases, we know that the speed is directly proportional to voltage. The speed of the machine starts increasing. Why the graph is increasing? Because slowly as I vary the potential divider from start point to the maximum point, the voltage across the armature starts increasing. As Va increases, then automatically the speed of the motor increases and reaches to a rated speed whenever a rated voltage comes across the armature. I will repeat. When the value of a resistance in the armature, that is the potential divider resistance, was zero, at that time the voltage across the armature was zero. Therefore you can assume the speed is zero. You can observe in the graph. As the resistance of the potential divider is increased, slowly the armature voltage increases. As the voltage across the armature increases, the speed of the motor actually it is increasing linearly, you can observe, and it stops whenever it reaches the rated voltage. So both the graphs, if you observe here, a resistance is included and we have discussed a linearly decreasing graph. We analyzed like a linearly decreasing graph. Here, whenever we have replaced the resistance with a potential divider, here also we analyze the same concepts, but a linearly increasing graph. A linearly increasing graph. In both the ways, what we can tell, the speed of a DC motor, shunt motor, can be controlled below the rated speed of the motor. Below the rated speed of the motor. So next he has shown for the same discussions, he has plotted a graph. Earlier the graph was speed versus armature voltage. In both the discussions, we have seen a graph has been plotted for speed versus armature voltage. Yes or no? Here he has plotted a graph For a speed versus armature current, that means for the load he has plotted a graph. Instead of armature voltage, he has taken a armature current as a reference. He has taken a armature current as a reference. So this one we have already discussed from the speed current characteristics. This one, this line, if you observe, the dotted line in the graph represent the no load speed of a DC shunt motor. The no load speed. That means when the load is zero, and the load is zero, irrespective of the resistance which is connected in the armature, irrespective of the resistance, when the load is zero, whenever the resistance is zero, you can assume the resistance is not there. Whatever the voltage we applied was coming across the armature, is coming across the armature. Whenever the rated voltage comes across the armature and the load is zero, at that time what is the speed? It is, I can tell this point, dotted line represents the no load speed of a DC motor, no load speed of a DC motor. So now this line normal, he has indicated a normal, that means when the load is varied from no load to full load, when the load is varied from 0 to maximum, from 0 to maximum or 0 to rated load is applied, at that time the speed is varying, representing a speed current characteristics of DC shunt motor. Here also the resistance is 0. This resistance whatever we have included in the armature is 0. When R is 0 and the load is varied, when the load is varied, at that time the speed of a motor is directly proportional to V minus IARA. Only the armature resistance drop will be present. Because of the drop, there is a small change in the speed. You can observe this difference. This difference is nothing but due to the IARA drop. Due to the IARA drop. As the load increases, the gap increases. At small loads, the gap is small. As the load increases to a rated values, then the difference increases. Difference increases. But still, if you observe the speed regulation of a DC shunt motor from no load to full load, it is good, which is less than 1 or 2% you can observe. The efficiency is more. Efficiencies. So now we need to analyze this graph with adding resistances in the armature circuit. How the speed of a DC shunt motor is varied when the resistance is included in the armature. Whenever resistance is added, you can observe I will get the third graph, that's this one with series resistor. That means at no load, the speed is no problem, it is the rated speed. Whenever the rated voltage is applied, the rated speed will come into the picture. As the value of resistance is increased to some particular value, if you observe, then automatically where the parameter, what you can observe, a more voltage drop actually takes place in the armature circuit. That means I am talking about V minus IRA, the voltage drops in the armature circuit. Here earlier I am talking about this difference. This difference was there because IARA drop was in picture. Here with resistor, if I add another drop will come into the picture. This gap is IARA. This gap it is IARA plus IAR drop. Therefore, this difference will come into the picture. As the load on the motor is varied, therefore automatically the armature current increases. As the armature current increases, the speed of the motor gradually decreases. This one we have seen from the speed current characteristics. There is no problem with this decrease in graph. That one we have analyzed with speed current characteristics. But here we have to concentrate on why the large variation of speed we are getting, why the regulation is increasing, why the difference is increasing. The speed control is increasing because of adding of resistance. Here only the IARA drop was coming to the picture. IARA drop was coming into the picture, but here the difference is IARA plus IA IAR drop. IAR drop is due to this resistance which is added in series. Then automatically we know that whenever the drop takes place, again the armature voltage decreases. Whatever the voltage I am getting in the armature, it decreases. That one we have seen in the previous graph. In the previous graph we have seen. So like this, we can establish the speed control of DC shunt motor with armature resistance method, or by including the resistance in series with the armature. Next, what are the advantages? Again, here also if you observe, it provides relatively smooth and easy speed control below normal value. Again, it is smooth and easy speed control because only we have included a resistance or potential divider in series with the armature circuit. Therefore, it is a smooth and easy speed control can be achieved, but it is below normal value, below rated speed of the motor. The speed can be controlled below the rated speed of the motor. What are the disadvantages? As entire armature current passes through the external resistance, there is a more power losses takes place because whatever the resistance which has been included in the armature, more amount of power losses takes place with respect to load. As the load increases, the current which is drawn from the armature increases. As IA increases, the same current actually it is flowing through the external resistance which is connected in the armature. Therefore, more amount of power losses takes place in the external resistance. This is one of the drawback. The second one, as the armature current is more than the field current, as the armature current is more than the field current, the rheostat required is of large size and capacity. Automatically, whatever the rheostat we are placing in the armature circuit, it should, the size of that should be more and the capacity of current handling capacity should be more. Automatically the cost increases because whatever the current which is flowing through the armature, or whatever the current which is flowing through the rheostat which has been connected in series with the armature is more, is increasing more with respect to the load. Therefore, the size and capacity of current handling capacity should be increased. The speed control above rated speed is not possible. That means here we have discussed only the speed can be controlled below the rated speed. Therefore, the above the rated speed we cannot control the speed of DC shunt motor by this particular method. The fourth point, due to the large power losses, this method is expensive, wasteful and less efficient because of power losses. Already we have seen with respect to the load current will be a rated value, then automatically large amount of power losses takes place. Therefore, it is expensive, a high value of rheostat has to be placed, it is expensive. So large power losses takes place and it is less efficient. This method requires expensive heat dissipation arrangements. As the losses increases, then automatically a suitable cooling arrangement for the dissipation of heat has to be arranged. Again, it further makes expensive. A large cooling requirement should be there in order to dissipate this heat to the surrounding medium. Therefore, expensive heat dissipation arrangements should be made. So up till now, we have seen the armature resistance control, or how the speed is controlled by the varying the resistance which is connected in the armature. We have seen now how the speed is controlled with the help of electronic devices. With the help of electronic devices. So here, if you observe the block diagram of the circuit, if you observe the block diagram, here all the parameters except the thyristor, it is familiar because already we have seen in electronics, we have seen what is the job of the rectifier which converts a AC voltage into DC voltage. A supply is a AC voltage if I consider, which is a sinusoidally varying voltage if you assume, then what I will get, the output of a rectifier is nothing but a DC voltage I will get. Let us assume it is a fixed DC. What is the job of a rectifier? Here, if you observe, a rectifier action can be done with the help of diodes. We have seen a half wave rectifier, full wave rectifier, and bridge rectifier. So different types of rectifiers we have seen. If you know, if you go through the operation, then the output of a rectifier will be a DC voltage. In order to get a pure DC, we will take the help of filters. Whatever the output of a rectifier with the help of diodes, we will get, it is a pulsating DC. So further, if we make use of a filters, then automatically what we will get? We will get a pure DC, a fixed DC we will get. Then when that fixed DC is given as a input, that fixed DC is given as input to the thyristor. Thyristor is a power electronic device which has got similar to the diode. Diode has got two terminals. Here it has got three terminals. One is anode, cathode and gate. So with the help of gate control circuit, here you can observe the term control circuit. Control circuit is nothing but he is talking about the third terminal which is present, that is a gate control circuit. With the help of this control circuit, here we are trying to vary the input voltage. We are trying to establish the control over the input voltage. So whatever the voltage, DC voltage I am getting, it is converted into variable DC. A variable DC can be achieved with the help of this thyristor. How it is achieved? With the help of this control circuit, with the help of the gate circuit, with the help of the firing angle. So let us assume if the voltage is 200 volts, so the output with the suitable arrangements of gate circuit with suitable value of gate current, what I can tell, we can establish, we can get a less voltage, we can control over the voltage. If I want 100 voltage, let us assume if I want a 100 voltage output, input is 200 volt, therefore a 50%, a duty cycle will come into the picture. A duty cycle, 50% duty cycle if we fix, then automatically I will get the output is 50% of the input, that is 100 volts. So whenever the voltage which is given to the motor is varied with the help of this thyristor circuit, whatever the voltage which is given input to the thyristor circuit is a fixed DC. But if the output, if you observe, whatever the output I am getting, it is a variable DC. As the output is varied with the help of firing angle or with the help of control circuit, then automatically the voltage which is applied to the motor, that is the armature voltage, what I can tell, the armature voltage is varying. As the armature voltage is varied, then automatically the speed of a motor can be varied. That means here the speed of the motor is controlled with the help of electronic devices such as thyristor and rectifier, what we can tell. Earlier it was electrically controlling the speed of motor, that is with the help of flux control method and with the help of armature control method. But here we are trying to vary the speed, or we are trying to give a variable DC voltage to the DC motor with the help of a solid state electronic devices such as thyristor and rectifier. So this is regarding the electronically speed control of DC motors. So let us see some of the MCQs related to the topics what we have discussed in the previous sessions, that is this based on the speed control. We have seen different types of speed control. One is flux control method, One is armature control method, another one is electronically speed control variation. So based on that, let us analyze. Consider the following statements. The speed of a DC motor can be controlled by the variation of, the first one is armature voltage, field current, armature circuit resistance, and angle of brush shift. So all the above three methods we have seen. By varying armature voltage, how armature voltage is varied? By variation of armature circuit resistance. So A and C are same. So by varying field current, if you vary the field current, the flux production varies. As the flux varies, the speed can be varied. Therefore, automatically the option, if you observe the answer A, B, C, you can consider all the three methods A, B, C. You can vary the speed of a DC motor. Following controls are considered for DC motors. He is telling following three methods are available, that is controlling the flux, armature resistance control, and the supply voltage control. Which of the above controls play significant role in the speed control of DC motors? Which method is important? If you observe, one is the controlling the flux. What he has told, by controlling the flux of a DC motor, that is a flux control method or field control method. The other one is a supply voltage controlling method. Supply voltage control method, that is the electronic speed control also you can take. That is option A and C you can take. Here it is not B, here it is E and C you can consider. A is flux control method, C is supply voltage control method. The speed of a DC shunt motor can be raised above its rated value by, above the rated value, above the rated value is nothing but the flux control method, that is the option B you can consider, inserting an additional resistance in the field circuit. By inserting additional resistance in the field circuit, the speed above the rated value can be achieved. In case of, if you go for option A, it is below rated speed, that is the armature resistance control method. Here it is flux control method. So here the question is regarding above the rated speed. Above the rated speed means we can go for flux control method. In armature control method, it is below the rated speed, below the rated speed. A DC shunt motor is supplying a load at its rated speed. The speed can be reduced. So right now the motor is running at a rated speed. How the speed can be reduced? That is with the help of, you can observe armature circuit resistance control method. Just as you have seen, the speed below the rated speed can be achieved by using armature circuit resistance method. Therefore, you can go for option A. The speed of a DC shunt motor supplying a load at its rated speed can be reduced. Again, same. The speed of a DC motor supplying a load at its rated speed can be reduced by connecting resistance in armature circuit, by connecting resistance in field circuit, by increasing applied voltage, any of the methods. Here you can observe that is how the speed below the rated speed is achieved by armature control method. The armature control method is nothing but by connecting an additional resistance in series with the armature circuit. You can go for option A. Next question. The most inefficient method of speed control of DC motor is inefficient method. That means it is option C. The losses, what we have discussed, the efficiency, the losses. The efficiency is less in case of armature control method and the power losses also more. Therefore, you can go for option C. That is the inefficient method of speed control is armature control method. That is option C. A DC shunt motor is operating at no load if the armature is shunted by a resistance. What happens to its speed? Its speed will, if the armature is shunted by a resistance, what will happen? Here the speed remains same. It does not increase or does not decrease because we have connected the armature across, we have connected a resistance across the armature. It does not affect the voltage. Whatever the voltage comes across the armature, it comes. There is no problem with the parallel resistance. Therefore, automatically, whatever the speed the motor is running, it remains same. It remains same. If there is a decrease or increase in armature voltage, then only the speed will vary because the speed is directly proportional to armature voltage we have discussed. But here there is no change in armature voltage, therefore the speed will remain same. The next question, the shunted armature method of speed control of DC shunt motor is. The shunted armature method of speed control, the armature control method is suitable for rapidly changing loads. Whenever the load changes rapidly, at that time you can go for a shunted armature method of speed control. The armature voltage control is considered and suitable for DC motor driving at constant torque applications. You can consider constant torque applications. If the voltage applied across the armature of a DC motor is reduced by 5%, is talking about VA. VA is nothing but the voltage across the armature. If it is dropped by 5%, keeping the load current and field unchanged, the load is constant, the field is also constant, field current is also constant. What happens to the speed? We know that the speed is directly proportional to armature voltage. As 5% reduced in armature voltage, the speed is reduced by 5%. Therefore, the option B, you can go for option B, the speed is reduced by 5%. In the armature voltage control method or rheostatic control method for speed control in DC motor, a variable resistance is where we have to add the resistance. In armature control method, the resistance is added in series with the armature, in series with the armature. In flux control method, we were adding resistance in series with the flux. So here for this you can go for option A, the resistance is added in series with the armature. Which method is suitable for speed control? Below and above the normal rated speed of DC shunt motor. In case of flux control method, we have seen the speed above the rated speed. In case of armature rheostatic control method, armature resistance control method, you have seen it is below the rated speed. So you can go for option C, that is voltage control method. By voltage control method, you can vary the speed above and below the rated speed of a DC motor. The small DC motors have best speed control by, so armature control method what we have discussed, it is suitable for small DC motors. Small DC motors have a best speed control by armature control method because the losses will be less, the load current will be less. Small DC motors if you consider, so it is suitable for small DC motors we can consider. In a DC motor, the armature resistance control is used to provide speeds dash rated one, above the rated one or below the rated one. In the armature resistance method you have seen, the speed can be controlled below the rated speed, below the rated one you can consider, below rated one. The next question, the armature voltage control is suitable if DC machine is driven at constant power you can consider. The armature voltage control is suitable if the DC machine is driven at constant power. So like this, in this particular session we have seen how the speed can be controlled or varied by the armature resistance control, and also we have seen how the speed can be varied by electronically with the help of a solid state devices such as thyristors. Thank you.